Yeah, okay.
Perfect. Great.
Great. Welcome everyone to the INQA seminar series. Today with us we have Anna Palacios, uh, and she'll tell us about the two local models on quantum annealers and their solutions.
All right. Thank you very much, Genia. So yeah, for those that attended AQC recently, this may be a bit repetitive because it's going to be a lot of the same stuff. But for those of you who haven't, and I hope you enjoyed this talk, and for those that did, I also hope that you enjoyed. I'm going to be talking about a scalable two-local architecture for quantum annealing for embedding all-to-all connected Ising models. Okay, so yeah, there's an archive already out, which you can check if you please. All right, so I mean, I don't really need to motivate much for this audience, but why do we care about scalability of annealers? Well, we want large-scale quantum computers, and well, we also want large-scale analog quantum computers, which are useful for real-world applications. And I'm going to be focusing on optimization. So I'm going to be thinking about classical optimization, which will be expressed as a QUBA model. And these problems, as you are probably aware, usually require full connectivity. But what is the issue with full connectivity? Well, the straightforward implementation of that, which would be just densely packing all the qubits with all the connections between them, it's really complicated. Not only for crosstalk compensation once you've actually built a device, which becomes an absolute nightmare, but just because also the larger, so the more couplers that you want to attach to your qubit, thinking about flux qubits, superconducting flux qubits now, by the way, I'm going to be thinking about these throughout the talk. Yeah, if you want to attach several couplers to this, to the qubit loop, you, for geometrical reasons, need to make it larger. And the larger you do it, the larger you make it, the more noise you're trapping inside this loop. So larger qubit loops essentially imply also less coherence of your qubits. Okay, so we're going to deem this dense packing approach just non-scalable for these reasons. Okay, so what solutions have people proposed for this? So you're probably also all familiar with D-Wave's approach of manual embedding, in which you just make up for the missing connect. So there's particular families of graphs with given connectivity, and within these graphs, you make up for the missing connections to describe your particular problem by doing short logical chains, ideally short logical chains that are ferromagnetically coupled. But also this minor embedding procedure implies an runtime overhead, but it comes with a perk that is robust to fabrication imperfections because you have many connections and increasingly more connections in new generations of these topologies that D-Wave is putting out. So more approaches to this is, for example, the L8Z architecture, which I'm sure, again, many of you are familiar with, which consists of this parity encoding. And so here qubits are representing parity between variables. So instead of having n qubits, you will have of the order of n squared. And this is like a nice proposal because with this parity encoding, it looks very nicely all this graph, and it gives you a planar structure, which experimentalists really love. But it requires 4 body couplers or ancillary qubits in order to implement the constraints to go back to the logical subspace. And this also implies a perfect fabrication yield for this device to work. So a failure in any coupler or in any qubit is going to severely impact, well, depending exactly on in which point it's made, but it's going to impact very much the sizes that you can achieve. So there's also actually more proposals by Genia here on paramagnetic trees, which is perturbative, and it allows you to simulate the entire transverse field Ising model. instead of just the problem Hamiltonian, which is what we are focusing here in this talk. And yeah, the energy scale goes as n to the power of 6. So here there's also like an energy penalty that will be limiting, as there is for the L8 set. Okay, so what are we going to propose right now? Let me start thinking about just a Z2 symmetric Ising model. We will include the local fields later. And let's think about, for this spin glass problem, which we are going to consider that it's all-to-all connected all the time, we can think about partitioning this all-to-all connected graph into individual triangular cells, such that we cover all the edges at least once. And once we are thinking about these individual triangular cells, we can think about describing the energy within each of these cells via two qubits, two physical qubits. And this we can do because we have this Z2 symmetry, so 2 qubits should be enough. And yeah, so we essentially have four energetically distinct configurations, which would be like the all parallel spins configuration, and then the three remaining configurations in which each of the three edges is the one that is parallel. Okay, so as I was saying before, if we choose a set of triangles in which to partition our problem such that we go through each of the edges of the original problem at least once, then we see that we can actually exactly represent the energy of the original problem by assigning like individual energies to each of these triangles such that they sum up to the energies of the original logical problem. And this essentially amounts to, like, if in the pre-partitioned problem we had this big J 1, 2 between qubits 1, 2, the triangles that involve this very edge, which here you see that it's two of them, the energies of these tiny J's 1, 2 have to sum up to the initial J 1, 2. Well, here I wrote the example with 0, 2, but you know what I mean. And yeah, importantly, we need to cover each edge at least once. So once we have partitioned the original graph in this manner, and within each triangle we have assigned a basis as we described before, then we can simply solve the linear system and see what energies, well, what couplings and local fields should be applied to those two physical qubits, such that they describe the energy of the logical triangle that they refer to. Okay, but describing just the energy of the individual triangles is obviously not going to cut it. We also need to make the information that these triangles are providing in our solution consistent with the original logical problem. So we need to impose some consistency conditions. And here, these consistency conditions are going to have to be imposed on shared edges. And I'm going to refer to these shared edges as interactions among triangles. Yeah, we're going to take the fixed choice of the all parallel configuration within each triangle to be the 0, 0 configuration for the qubits that describe that particular triangle. And yeah, as what you can see in this plot here to the left, with the binary numbers on each edge, is just a summary of which. I don't know if you can see my pointer actually. Can you see my mouse?
Yes, we can.
Perfect. Good. Yeah, so essentially pointing to the fact, so for example, this 0, 1 here means that this would be the parallel edge corresponding to the configuration 0, 1. So once we have defined this within each triangle, we're going to take a closer look at this edge here. And we see that for the orange and green triangles to be consistent with each other, it has to happen that these two configurations in the orange triangle correspond to these two other configurations in the green triangle, and well, the rest correspond to the rest. Just by visual inspection, you can see that this simply corresponds to a ferromagnetic interaction established between the first qubit of the orange triangle, the first physical qubit of the orange triangle, and the second physical qubit of the green triangle. And so we come to the realization that this is just a too local constraint. And yeah, once we do this for each of the shared edges, we realize that the physical graph that corresponds to this logical click would just be a 6-qubit chain that looks like this. Okay, so with this, let me point out that the 1-1 edge, because of the 0-0 choice that we made before, the 1-1 edge must always be chosen such that it's non-interacting to maintain this two local constraint. But once we do this, which we can always do, and yeah, I will talk about a way in which we will do it later, then you have this mapping between a logical all-to-all connected problem onto a physical problem that you can potentially embed in your device that is way sparser, as you can see, and just involves the cost function, which is given by the individual triangle energies, which we defined before, plus the constraints that make them consistent. So again, you can quickly realize that you can choose these sets of triangles in many new ways. So we're going to set an algorithm to choose these. And this consists on selecting a reference node. And you can think about starting from the 4-click that we had before. And then you just increasingly add new qubits. And for each new qubit that you add, you have to connect it to all the rest. And the triangles that you use to do that must always go through the reference node that you selected at the very beginning. And by doing this and ensuring that the edge energies are included fully in the first triangle of appearance, remember that they always have to sum up to the energies of your original problem, then you end up with a nice structure like the one that you see here to the bottom right, where the triads of blue numbers refer to the triads of logical qubits that the closest to physical qubits are describing. And yeah, this is the J's here that you see are just the ones that end up being here by this rule of including edge energies on the first triangle of appearance. So if you look more closely, you see that the constraints are actually generating like a very nice structure on this graph. And you see that you ended up with a bunch of nicely braided physical chains. So once we went through the set to symmetric example, let me very briefly go through how you would include local fields to this. So yeah, from the 4-click example that we saw before, you can simply collapse the strongly coupled ferromagnetic links and see the effective 3-qubit model that this would describe, which is just, well, since we had a 4-click before, but we had inversion symmetry, this is essentially with that symmetry removed. And now you can use this very scheme to include the local fields by considering that one of those n equals 4 qubits was fixed, and then you end up with something like this. So now your triangle energies are described by 3 qubits instead of 2, but you can simply add this new sign information by an additional sign qubit, which will split the energy of these configurations, and you can just solve the linear system as we did before. And you end up and if you use the same rule as you used before, that for each new node you incorporate the local field only on the first triangle of appearance, then you realize that there's a bunch of sign qubits that are not connected to the respective triangle, so you can just remove them, and you end up with a scheme that looks like this, in which, if you look at it closely again, you see that the logical chains that we had before are still there. So this would be this, and this would be this and this, and we just added an extra one. And I didn't mention this before, but notice that these logical chains, the ones that are not referring to the sign qubit, so the ones that we had before, are just the parities between the reference node that we selected in the triangle choice, which in the example that I showed before was node 2, So here you see that these logical chains would carry the information of the parity between node 2 and node 0, node 2 and node 1, and so on and so forth. And the additional chain that we just generated, it's just carrying the information of the orientation of the selected node. Okay, so this is kind of like a mixed parity and single qubit encoding. It's just like a transformation of the original Ising problem. So from this full graph, we see that it's very, very sparse. It has a degree of 3. The number of qubits that it requires goes as n squared, and the number of couplers as well. All right, so that was a nice sparse construction. We like sparsity because it allows us to reduce crosstalk as much as we can from a hardware perspective, from a design perspective. And yeah, also noise in the sense that we can keep our qubit loops smaller. And this, as you can see, it's like a very easy to serialize structure. Actually, we could take this chain here and put it just below. So if we allow each chain to be 1 qubit longer, we could make this perfectly regular without this asymmetry caused by the sign chain. So this fabrication is serializable. That's good for scalability. Now, what about the scalability of the algorithm? What about the fact that now that we are embedding our problem in a way larger Hilbert space, our gap may decrease with the size of this new Hilbert space instead of the logical space? This is not addressed yet. And also, what about the million-dollar question, the scalability of constraints? So in order to actually enforce those constraints satisfactorily, we will need to increase the coupling as we increase system size. This is the same problem that, actually any embedding scheme runs into when you want to constrain yourself to a lower dimensional part of the Hilbert space. So in this case, we start with some advantage with respect to, for example, the L8Z scheme, because here we're dealing with 2 local couplings of the ZZ type, and superconducting qubits already naturally have a larger ferromagnetic coupling than they do antiferromagnetic, but this will also have a limit. So we want to think about how we can try and mitigate this. Yeah, we're going to be focusing on this. By the way, I cannot see the time, so if I go way over time, please stop me, Genia, or tell me something. And by the way, anyone that wants to ask any question at any time is welcome.
Oh, since we started late, you have plenty of time.
Okay, good. All right. So how would we ideally go about this, not having to care about the scalability of coupling constraints? So ideally, we could follow this work by Hen and, well, some others that followed, but this line that was started by Tai Hen, in which you consider that you have a constraint operator, the one that is describing your constraints, and if you manage to have it such that both your problem and your driving commute with these constraints, while your problem and your driving and your driver still don't commute, then you can actually get away without any constraints, right? Because your logical subspace and the rest of the Hilbert space are not connected. So that would be great. But actually, for the logical subspace that we have, that remember that it's like the all 0 or all 1, and the space spanned by the all 0 or all 1 configurations on each of the chains. This turns into something highly non-local inevitably. And even if we could build this is actually not trivially connected to the transverse field. So just starting with the sigma x, so even preparing the ground state of this Hamiltonian is not trivial. Okay, so what can we do in practice? So the way that we can try to approach the ideal scenario as much as possible is trying to implement a bias towards the logical subspace, and then hope that some diabaticity during the evolution will keep us close to the logical subspace. Okay, so we're gonna try to do this. We're gonna prepare the standard transverse field driver. We're going to anneal to a bias driver, to a biasing driver, and then we're gonna anneal to the problem Hamiltonian. All right, so what are the candidate biasing drivers? The first choice that comes to mind is the transverse field Ising model. It is readily available in your device if you could do all the previous stuff. So that's nice. And also, this is a very well-known model. It's think about the fact that we are considering single chains, so this is actually analytically solvable for single chains. And we know that as this JZZ approaches 1, the ground state will approach the G8Z state, which would be completely contained in our logical subspace. And the issue is that there is a quantum phase transition as at JZZ equals 1. So as we go to larger system sizes, our gap will vanish. And this limits how much we can approach this logical subspace. What can we do to try to go around this for a bit? We can introduce some additional XX terms, stochastic in this case, and end up with an XYZ model that kind of looks like this. And we're just going to consider these XX terms to be alpha times the JZZ. And this kind of allows us to play a bit around with the size of the gap that we had before, because we can kind of tune this critical JZZ, and thus achieving larger biases for the same gap. All right. So how can we try to quantify this? So as the Hilbert space grows exponentially, the projection onto the logical subspace will decrease exponentially. So we can write this down kind of like this, and you see that this corresponds very well with numerical summation. So this is DMRG calculations for n equals, well, for different n's that you have here, of course. And yeah, if we take a look at this particular exponent that goes with the system, with the chain length. Now L is the chain length. We can devise this coefficient beta, which we're going to call the bias, and we're going to define it as this zeta minus 1. Why this minus 1? Essentially because for the standard transverse field driver, this is 1, and that would correspond to a completely unbiased initial guess, so that's why we're subtracting 1. So, and again, for the reasons that we explained before, the greater the bias, the smaller the gap, and there's a trade-off. Okay, so we can try to look at how this bias looks versus the gap in the thermodynamic limit for different values of alpha and for the transverse field model, and we essentially get something like this. Again, this is DMRG calculation, so this is like the exact gap in the thermodynamic limit, and then these for the different alphas, since this model is not exactly solvable, we did some extrapolation. So the crosses that you see are the gaps obtained for a chain length of 100, and the dots are the extrapolated values. And you see that for example, a gap of 0.3, which would realistically correspond to minimal gaps of about a gigahertz. And again, thinking about superconducting qubits, so this would be like a realistic number of a more or less limit that you would maybe want to set on how small your gap can be. This gives you like a bias of a factor 2 for the transverse field Ising model, when you can get biases up to a factor of more or less 5.5, depending on your alpha, for the same values. And the catch here is that these increasing alpha doesn't come for free. You do need to increase your coupling strength to achieve those biases. Okay, so I'm gonna wrap up. We presented an alternative approach for scaling up quantum annealing processors, which consists essentially on efficiently braiding logical chains. This graph that is generated is maximally sparse, and it's also too local. But it has the downside of requiring a perfect fabrication yield, which is not a technology that we have just yet. And also, again, as any other embedding strategy, requires strong ferromagnetic couplings. Yeah, the number of qubits scales as n squared, as does the number of couplers. And also, we think it's nice that the simple structure of the logical subspace allows us to think of simple driver Hamiltonians to try and mitigate the scaling of the coupling constraints. And that's it for me. I will be happy to listen to your questions now.
Thanks for the great talk. Please feel free to ask questions. Very well. So I guess I will ask a few as well. So one of the interesting ideas in this work for me, from my point of view, is this idea of triangles. So I was curious if there is a kind of if there is an algorithm based on your idea of triangles that can come up with a graph, a embedding graph for any logical graph, not just all-to-all graph.
Uh, I mean, from this all-to-all construction, you can get to any graph, because if it's not all-to-all, it's just eliminating couplers. And then what you're effectively doing is like chopping off your final diagram. And
So you actually will get a smaller embedding if your graph is not all-to-all. Whereas if you just use chains for qubits, then it's just n squared in terms of your number of qubits, even if your graph has a lot of missing links, right? So I think this is a great contribution. So now, uh, Aviv, I think you have a question.
Hi, Anna. Yes, the n to n squared is interesting to go from, because if you do, I'm thinking measurement-based quantum computing now, that's a mapping between gate model register qubits, where you can do gates between any qubits. So you need at least potentially an all-to-all coupling possibility. But then it becomes local in the measurement-based quantum computing graph. So I mean, that's not why it's done that way, but that's what happens there. So I'm wondering if there's something quite general here, that if you want to go between arbitrary to planar, local, like, local planar, or like reduced, I mean, okay, so it's not, the measurement-based graphs would normally be, and they wouldn't normally be 3 local or 2 local the way you've done it here, but they could be made so locally. The point is then you now only need nearest neighbor interactions rather than long-range ones. So I'm wondering if there's just some general graph theory behind all this for the resources you need to achieve some of these things. So did you get any of this stuff from graph theory, or was it really just like you managed to make this work, just sort of inspiration on what you were doing?
It's, yeah, quite inspirational. So yeah, it was just following this construction of the triangles that I arrived to this graph. I'm unfortunately not very familiar with measurement-based quantum computation, so I couldn't quite follow what you were meaning. But I would like to stress that this is because I did get asked this question before. So this is a repetition code in the end. So if you go, yeah, because it's logical chains that are ferromagnetically coupled, right? So you cannot go beyond encoding classical Hamiltonians with this. I don't know if that contributes to what you were thinking.
I don't think so, because I think this is graph theory related rather than quantum.
Okay.
As in, I just as in just how you map something with higher connectivity to be more local. I mean, essentially, the measurement-based quantum computing, the simplest way is just a Cartesian lattice. But then it's like you have repetition code in the sense in that your qubits are progressing along one direction. So say the x direction, and all the y connections are effectively your gates. But as I say, the way it's set up, you end up being able to move the information such that you don't need the long range. You're doing the long range correct connections in the graph rather than by moving qubits around. But yeah, so I don't think, as I say, I don't think it's a quantum specific thing. I think it is topological graph stuff, and there might be some benefit from talking to people that work on graph theory, and they might be inspired to look at some of the problems we're working with.
Yeah, thanks. I will definitely.
They may not have asked questions like this before because they didn't know they were interesting. But yeah, that was my thought, that the fact that you're coming out with the same scaling is probably not at all accidental.
I think so. I will definitely look into it. Sounds quite interesting. So, I mean, what I can say about, well, it's not fully graph theory, I guess, but yeah, d equals 3 is the minimum that you need to inquire NP hard problems, right? So in that sense, this graph that it results here is minimal.
Yeah. No, it's very cool stuff. I didn't get to see your talk because I'm organizing, so I'm very pleased to see it.
Nice, I'm glad.
Very well, thank you. Are there any other questions? So I guess I would be curious if you had a chance to look at some ideas about the Rydberg atoms and trying to make a quantum annealer out of those. They seem to struggle because they can't really make a non-planar graph that easily, but there was at least one paper that proposed a possible way of doing that. So I was wondering if you looked at that and checked if your idea is compatible at all.
So I unfortunately did not look into the papers of, well, I'm not sure it's the same thing that you're referring to. I did think, okay, two things. I did think about whether you could do this with neutral atoms, and the issue is that you don't have ferromagnetic couplings, right? So this gauge that you would have to do in order to get the same effect wouldn't really work because it has to be consistent throughout all the chains. And then, yeah, I couldn't see it happening. About the non-planar stuff, the papers that are on my reading list are how they adapted these LHZ schemes for neutral atoms as well, how they managed to make this effective four-body couplers. I think there's some work on that I didn't get the chance to read just yet, but that I learned about in Glasgow, actually. But I will add the non-planar stuff to my list as well. I mean, there are...
I'm using non-planar very broadly, so I didn't mean it rigorously.
Okay. Okay. So yeah, I'm unfortunately not very well versed on this, but yeah, my thought is that you cannot apply this to neutral atoms, unfortunately, because that would be, yeah, since it's easy to scale.
Yes, so or else life would be too easy. Right. Thank you. I think this is a good place to stop the recording. If there are no further questions, I can do that now myself, but if it's possible, yeah, that's good. I would say that the statement in the second part of the talk about the GHD state and what's happening exactly at the phase transition seemed a little bit strange to me, so maybe one double check on that. or if you want, you can follow up with me kind of in the email.
Okay.
So
Sure, I would love to discuss this.
yeah, but with that, thank you all for coming, and yeah, see you next week.
All right. Thank you all for attending and for having me. Bye.